Welcome back, everybody. In this video, we're starting with a group G and an element X in G, and we want to show that X has a unique inverse element. This is one of the foundational results in basic group theory, that we have unique inverses and, well, unique identities, in fact. So let's see how we could do this. We'll show a couple different approaches. One way is the following. So let's assume that we have a second inverse. We'll just make it easy. We'll call them, say, y and z. So assume y and z are inverses for x. Then I know that the identity element is equal to y times x. It's also equal to z times x. Now, if we assume the cancellation property for groups, so by right cancellation, so you notice I have in this equation an x on the right side. I can cancel it. So by cancellation, z is equal to y. So that's one proof. If you don't want to assume that you have cancellation, which there's no reason you shouldn't. I mean, really, what am I doing? I'm just multiplying both sides by some x inverse, right? Which could, in fact, be our y or our z. But let's try it without that. So let's again start with some z, say. I know that z is equal to z times e. And I also know that e is equal to x times y. Now, because I'm in a group, I have associativity. I can write this as zx times y. And I know that z times x is equal to e. And so I get e times y, which is equal to y. So once again, z is equal to y. All right, no matter how we do it here, it's a fairly easy proof. But I want to make one extra point, which is a very common thing you want to do is write your proof in the following way. Let z and y be inverses such that y is not equal to z. So you're trying to set up a proof by contradiction. Now you go through all the same steps, and you end up showing that z is equal to y, and you say, hey, that's a contradiction because I assumed that they were not equal to each other. So this is one of those many instances in elementary mathematics where you want to prove something and you said, oh yeah, proof by contradiction is a great way to do it. And in the middle of your proof by contradiction, you've actually proved the result directly. Right? If you just cross out this line, you have a direct proof. Right? Cross out that contradiction at the end. So this is something you should be looking out for, is when in the proof of doing a proof by contradiction, you're able to just get rid of the assumption that it doesn't work, get rid of the contradiction, and then you still have a direct proof. Very common thing that happens.